I'd like to welcome you to the CERIAS Security Seminar for January 21st. Today it's my honor to introduce Paul Kidwell, who, in addition to being a PhD candidate, is also a Purdue alumni, having obtained his bachelor's here in 2000. After that, he joined the real world for a while before getting a master's at DePaul and then returning here to work on his PhD. He's doing work in analysis of rankings. And today we're going to hear him talk about an algorithm for keystroke detection, showing some of the limits of what we think may be secure, otherwise think would be secure information. So,
thank you.
Paul.
Thank you very much for having me here this afternoon. Recently I've been working with Professor Cleveland, John Girth, and Saptarshi Guha, who's here this afternoon also, on developing a rules-based statistical algorithm for keystroke detection. And so that's what I'll talk a little bit about this afternoon. So what are we getting at here? What are we really trying to do? Well, we are looking for SSH logins, and those SSH logins that we're interested in are those that are interactive sessions where you have a human typing on a keyboard. So what we're looking for are keystrokes, and that's kind of the goal of this algorithm. We want to be able to identify any sort of keystroke packet in an SSH login. And so there's, as far as where this fits into the framework of things, there have been some previous approaches to this where people have looked to classify connections as having keystrokes or not keystrokes. And some of the work that's been done, for instance, Paxson and Zhang took a look at the ratio of small packets to the total number of packets and the inner arrival timings with those packets. And they did all right there. And Wegman used a nearest neighbor approach using packet counts, whereas Hernandez Campos used a partitioning and divided each connection up into a sequence of packets. And these packets were there were three modes of activity: bulk, transfer, interactive, and one other, I believe idle was the third category. But the common thread amongst all of these methods for classifying connections that have keystrokes is each one of them used a connection summary type statistics and looked at things that summarize the connection. And where we felt we might be able to do a little better here is we take a more granular approach and looked at the packet level detail and worked from the packet detail upward in order to come up with an alternative method for identifying keystrokes within SSH connections. So what we've got here is a rules-based statistical algorithm. The name comes from the fact that the rules-based portion of it comes from the fact that we use some of the domain knowledge of TCP and SSH and how they behave to construct some rules. Whereas the statistical algorithm portion of the name comes from the fact that we're looking at the distributions of some timings and packet sizes and such. So the goal that we're explicitly trying to get at here is we want to identify packets in any TCP connection that are client keystrokes of an SSH login. So whether this is running on port 20, whether this is a connection using port 22, or whether it's a connection using another port, if there's an SSH if it's an SSH connection, we want to be able to identify the keystrokes there. Our approach to this problem has been a two-pronged approach. The first step was we wanted to develop visualization tools. And these visualization tools should allow us to see keystrokes. We wanted to plot these connections in a way that we got a feeling for what is happening, what characterizes a keystroke, what are the distinctive features. And then we translated those learnings into a algorithm for classifying each packet as a keystroke or not a keystroke. The input to our algorithm here is are the packet arrival times from the network monitor, and also the TCP IP headers from each one of the packets in a connection. The output's going to be, there's two levels of the output here. The first level is each packet in a connection is going to be classified as being a client keystroke packet or not, and the second level of output is going to be at the connection level. each connection will be classified as containing keystrokes or not containing keystrokes. So the properties of this algorithm that make it a nice algorithm here are, one, it's passive. We don't have to inject any packets into the network traffic. Two, we don't employ any knowledge of the packet payload, so we don't look at the payload at all. And three, it seems to be fairly accurate relative to some of the previous work here. So to give you an outline of where we're going today, the first thing we'll do is we will take a brief look at some of the protocol background and how this impacts how we designed our algorithm. The second thing we'll do is we'll take a look at the data sources we used for this project. Third, we'll go through some examples of the visualization tools and look at exactly how we were able to see these keystrokes. The fourth thing we'll do is we'll walk through the algorithm step by step, and finally we'll take a look at the performance here. And feel free as we go through this to ask any questions along the way if there's anything that's not clear or you have any questions. So to get started here, the background protocols. Protocols shape the form of TCP packets. And for the purpose of our discussions here today, we're going to define a keystroke to be the first client data packet sent when a person using SSH presses a key. So that key will generate a sequence of packets as in part because of SSH and in part because of TCP. But that sequence of packets we'll refer to as the keystroke packet sequence. And so for an example here, a standard keystroke packet sequence would begin with a client data packet that contains the data of that particular keystroke. So if you press K, that K will go across to the remote server. In turn, that K has to come back to be displayed on your monitor. So that will again be transferred back as a server data packet and displayed on your monitor. And TCP stipulates that there will be a response, that the reliability mechanism stipulates that there will be an acknowledgement of that data receipt. So a standard keystroke packet sequence will then be a client data packet, a server data packet, followed by a client acknowledgement packet. Additionally, SSH stipulates that all of these data packets have to be of a particular size, or at least all of the client data packets have to be of a particular size. They will be multiples of 4 and between 8 bytes and 252 bytes. And that's due to the encryption there. So as far as this goes, you'll also have some other type of keystroke packet sequences that will arise. And for example, when someone's typing quickly, or perhaps there's a long distance between the server and the client machine, you might have a situation where you have a keystroke packet sequence that consists of a client data packet followed by a server data packet, where that acknowledgement packet is actually lumped onto the following keystrokes initial client data packet. So I think that gives you an idea of the terms that we're working with here as far as what we're looking for and what a keystroke packet sequence is. So the data that we worked with, we used 4 different packet traces here to conduct our development and testing. The first packet trace we used was the Leipzig data set. And what that is, it's a collection of a packet trace consisting of a whole lot of connections out of the University of Leipzig back in 2002. We used the second 54 hours of this data set and took all of the SSH connections out of there. So there were 9,077 SSH connections there. And we ended up making a whole lot of plots and using them to develop our visualization tools. We needed a lot of connections of diverse behavior in order to figure out what was characteristic of these SSH connections. So that was primarily of use in our developing visualization tools. The second set of packet traces was built by ourselves using the machines in Purdue Statistics department. So these were manual, what you'd call groundings, things that we knew exactly what was happening. So every keystroke that we typed, we could assign a particular meaning to it, whether that was me typing ls or whether that was me pasting a piece of text into the into the onto the prompt, we knew exactly what each activity was, so it gave us something known to work from. And in constructing that, we also had connections that were not directly from campus to here. We had connections that went across the country and back in order to introduce some variability as far as the timing at longer round trip times. The third packet trace consisted of some, again, Leipzig data, but these were connections that we went through using the visualization tools that we developed. And we call them all, you could say they were almost known, because you could go through and the visualization tool is powerful enough that when you look at it, you can get even though it might not be detectable in some sort of a regression or something, your eyes will be able to tell you, there's definitely a signature to these keystrokes, and your eyes could tell you that this is definitely a keystroke. So we went through and manually created some groundings in that sense. And finally, the fourth set of packet traces we used were collected from Purdue Statistics department. These were connections that went from the department to the outside. So from the department to outside of Purdue, and from outside of Purdue back in. And there were 110,000 of them. They were collected over a 24-hour period, and we used those for some of the testing that we've done to this point. So the first plots I'm going to show you here were some things that were made in the very beginning to give us an idea of where to go. And this is a very high level plot, and what you have here is a cumulative bytes versus duration. And in this is a interactive connection with 37 keystrokes in there, you see. And what stands out mostly about this plot is that you have the two lines that seem to be very close to each other, and that indicating the number of bytes going in each direction. And down here in the third panel, you have these red dots corresponding to where our keystrokes are located in here. But what this is really saying is that when you have keystrokes, you have roughly the same amount of information going back and forth. So an interactive connection, you're going to expect to have the same amount of information going in each direction. And that was definitely a signature that we were able to pick up on using some of the higher level plotting tools. Whereas, and we were able to take this and use this to refine and build our next stage of plotting tools. And the series of plots I'm going to show you now are where we actually kind of got into the nitty-gritty of how do we see these keystrokes. And this is an example of a low-level plot, and these are specifically known activities. So this was actually me sitting in the statistics department, logging into one of our machines there, and you can see as we go through here exactly what happens in this connection. So to give you a little bit of the lay of the land here, the circles here, the red and the blue circles correspond to packet sizes. So this red packet would correspond to a client packet with 100 bytes of data, whereas this blue packet would correspond to blue circle would correspond to a server packet with 52 bytes of data. So red signifies client, blue signifies server. And as you look through here, it looks like kind of a mess for the beginning, and that's the SSH negotiation up to about packet 38 or so here. And once you get to packet 38, you start to see that client data, server data, client acknowledgement sequence that I mentioned that was a standard keystroke sequence. And you look at it and you say, all right, well that's kind of what we expected to see. That's nice. We see two of these are the same size, and then there's a packet containing no data, which is exactly what we'd expect. You go on and you see another one, and you see another one. And that's me typing ls and hitting return. Whereas you come down here, this packet corresponds to pasting some text into the at the prompt. And finally, I type ls again, and you see that these packet sizes are maintaining that standard form. And then finally, I type exit and close the connection. So that gives you an idea that we've got our packet sizes here that are coming out as we expect. But what's more important is that when you look immediately up from each one of these packets, here you see there's a yellow diamond that falls immediately above that client data packet. And that yellow diamond is plotted against the right-hand scale here, which is a log base 10 of inter-arrival time. So this log base 10 of inter-arrival time, these inter-arrival times that we're using here, let me step back one moment and say the inter-arrival times are between consecutive data packets from the same source. So for instance, if you have a client data packet then you're going to have, eventually you'll have another client data packet. That inter-arrival time, based on those two packets, you take the log base 10 of it, and that's what the yellow diamond corresponds to. The green diamond here would correspond to the inter-arrival time, the log base 10 inter-arrival times computed using only the server data packets. And so what the nice thing that we see here, though, when you look at this plot, is you see that as you look at this first keystroke here, you see the yellow diamond and the green diamond very near overlap and are almost at the exact same height. And you look at the next keystroke and you see the same thing. And you see the same thing. And as you go through here, looking at each one of these things, when you see a keystroke, you see a pair of the yellow and the green diamonds. And what that signifies is that we have a strong correspondence between our inter-arrival times based on the client data packets and their echoes from the server. So that was kind of a key finding here, and it was a signature that's used when these keystrokes get a little messier. As far as other difficulty that we see, depending upon your implementation here, you have keystroke packet sequences of varying forms. So for instance here, again you see some regularity in form here. There's a client data packet followed by a server data packet, server data, to client acknowledgments, and so on. As we move through here, you see again this is a 5-packet sequence: client, server, server data again, to client acknowledgments. And what this gives us here is we've got a 5-packet keystroke sequence instead of the standard 3-packet keystroke sequence. And the nice thing is, though, they're all initiated by a client data and they always have an echo to them. But especially telling here is, again, we have our diamonds lining up nicely. So you have those the client and server inter-arrival times line up very nicely. So that's, again, a key in identifying it. Even though the implementation in your keystroke packet sequence form has changed, the timing still remains the same. This is an example of mouse movement here, which comes out to have something that looks very similar in the fact that we've got a lot of packets of the same size. So we've got a lot of client data packets followed by server data packets. And we've got a lot of yellow and green overlapping diamonds. But these diamonds they're a little lower than the diamonds we've seen in the past. And that goes to the significance of what this gray band is here. This gray band that you see here corresponds to typing rates between 200 words per minute and 10 words per minute. So the bottom the bottom edge of this would have inter-arrival times that project to a typing rate of 200 words per minute, and the top would have typing rates that project to inter-arrival times that project to a typing rate of 10 words per minute. So when you see inter-arrival times falling in that band, it's a good sign that we're onto some keystrokes here. And these are just a little bit low, so it's a little too fast, and it's probably signifying that we're dealing with something that may be more an automated type communication or interaction here. Finally, this is an example from the Leipzig data, and it goes to show kind of how we can take what we've learned from some of these standard connections and extrapolate a little bit. So what you see here is what appears to be an SSH connection, and when you look at it, we start here and we see, say, a packet 38 there. You see kind of what begins to be the standard sequence as far as client data, server data, client acknowledgement, followed by, here's a short sequence of client data, server data, followed by client data, server data, client acknowledgement. And so we've got a little variability in the form of the keystroke packet sequences, so clearly you can't use that. But the nice thing that we see here is, again, you have these diamonds lining up very nicely in these inter-arrival times. So the consecutive inter-arrival times turn out to be a very nice thing, very nice tool here, and when you couple them with the packet sizes. So this is a very strong indication that we'd be dealing with some sort of an SSH connection here. So to summarize, what we were able to learn from these visualization tools is there's some fundamental characteristics that are going to help us out to identify keystrokes. One, all these keystrokes are going to occur in groups. You aren't going to have someone just typing a K by itself is not going to do anything for you. So we're going to have keystrokes in groups. Second, every keystroke packet sequence has to have we know it has to have an echo in it. So that's the second feature that we exploit in our algorithm. Third, our echoed packets are going to share very distinctive timing characteristics, as we saw with the overlapping diamonds, and so we can exploit that. And fourth, the form of the keystroke packet sequence is going to be approximately constant locally. And by what I mean when I say this is that although we'll have slight variations, for instance, we had the standard form followed by the standard client packet, or client data packet, server data packet, client act, followed by client data, server data. That was a 2-packet sequence. These forms are still approximately the same because the amount of data in both those client packets were the same, and the amount of data in both those server packets were the same as those client packets. So you may have a little variation, but those sequences are going to be approximately the same. And finally, we see that the inter-arrival times tend to correspond with a typing rate consistent of 10 to 200 words per minute. So we exploit all of these ideas in the development of our algorithm. So to more formally state what we're doing here, what the rules-based statistical algorithm does in terms of response and predictor variables is we take each connection, and it's comprised of a series of packets. Each packet is indexed, corresponds to an index I, and this I runs from 1 to n, which is the total number of packets in the connection. The response variable that we're looking to predict here is going to be f sub I, and that is an indicator variable that just identifies a packet as being the first packet in a keystroke sequence or not the first packet in the keystroke sequence. So it'll be 1 if it's the first packet in a keystroke sequence. So, and finally, the predictors that we use here, D, the bytes of data in a packet, the source of the packet, we need to know which direction it's coming from. Is it coming from the server, or is it coming from the client? And the inter-arrival times, which are the log-based 10 inter-arrival times between consecutive data packets from the same source. So this is undefined if it's an acknowledgement packet, there's no data in it. And additionally, we'll use the index I and the TCP flag for in the algorithm as well. So how does the RBSA work? There's a total of 4 steps here. The first step is we want to identify those packets in a keystroke sequence that are candidates, we do some preliminary screening. What packets can even be candidates to be keystroke packets? And so that's our first step. The second step is we need to divide this connection into a series of epochs. These epochs correspond, you may have a Emacs screen being drawn, and that's going to look a lot different than someone typing. And you can have a variety of different activities within a particular connection. So we need to be able to break it up into segments that have similar behavior. Finally, the third step here is we apply a classification tree to each epoch to come up with a classification for that epoch. Are there keystrokes in here, or are there not? And finally, we employ an iterative procedure in order to refine our classifications. So the first two steps that we deal with here are the candidate packets and the epoch partitioning. So identifying the candidate packets, well, there's going to be a number of things that we can do here. Number one, it has to have been from the client, so that's where directionality comes in. And these are basic exclusions. 2, it's got to contain data. 3, the inter-arrival time. Well, if it's typing, that can't be too fast. So there's a tuning parameter set there to exclude things. It can't. As I said, it can't. Also, TCP flags. We can't. A center or a fin packet would make no sense to be the first packet in a keystroke sequence. So those are some basic exclusions that we use, and there's a few others, but those are basic exclusions that we use to get down to a set of base candidates to work with. So these are packets going in the right direction that have echoes and are generally the right size. Secondly, how do we distinguish our epochs? Well, once we've got these candidate keystroke packets, we look through our connection, and we know these keystrokes have to occur in fairly close their proximity has to be, well, they have to be fairly near to one another. There can't be too many packets in between consecutive keystrokes. And we observed empirically that the 7 seems to be a fine number, that if there's more than 7 packets if there's more than 7 packets following a client data packet, well, let's start a new epoch, because this may be the beginning of a new activity, because there's not going to be a keystroke that's 7 packets. So that's how we define our different epochs. Once we have our epochs in place, it makes sense to start looking at our how do we classify our epochs. So the way our classification works is we're going to have a set of candidates within that particular epoch. This set of candidates is going to, the set of candidates that we have is going to, they'll all either be classified as keystrokes or they'll all not be classified as keystrokes, depending upon the behavior of that epoch. And there's three variables that we come up with that seem to do well for us as far as determining the behavior of each epoch. The first is Prop 200 here, which is the proportion. Is the first thing we look at, and is the proportion of the inner arrival times that project to a typing rate of less than 200 words per minute. So, as long as there's a large proportion of the packets within this epoch that are at a reasonable rate, well, that's a strong predictor that we're dealing with something that's an interactive type activity here. The second thing we look at is similarity. Each one of these candidate keystrokes, the first packet in the sequence, there's going to be some packets that follow after it, and those are going to form a candidate keystroke packet sequence. And there should be a lot of regularity between the forms of the consecutive keystroke packet sequences. For instance, we'd expect if client data packets are running at 80 bytes, we'd expect that they should be at 80 bytes throughout that epoch. We wouldn't expect to see an 80 byte client data packet followed by a 100, followed by a 50. That would not make sense. So we want to see similarity in the forms of the keystroke packet sequences. And this metric here describes exactly how that works out. What it does generally is it compares the size of the first two packets in each proposed sequence, and then it also adds to it based on the difference in lengths between the two proposed sequences. And that gives us a similarity metric. And finally, we use a variance within the epoch. So we look at these inner arrival times, and they were plotted on a log-based 10 scale. So it looked like when we saw the mouse movement that they jittered around about as much as the keystrokes. But what we do here is we look at the actual variance, not the log-based 10 variance. And so there's actually a much smaller variance within those automated connections than those connections that are actually a human typing. There's going to be a much higher level of variability within the human-based activity. Finally, a little more detail on the fourth stage here is our iterative prediction mechanism. What we do is once we've classified all the keystrokes within the epoch based on our classification tree, at that point we've learned a form of the keystroke packet sequence, and that form is just the mode of all the different keystroke packet sequences. And we can go back through, and there are some candidates that we might have missed due to odd timing, and you go back through at that point and you can compare each potential candidate that you missed with this particular known sequence now and make a correction based on that. And secondly, once we've made these predictions, we can go through and eliminate isolated keystrokes. You aren't going to have one keystroke by itself, and that doesn't make any sense. And so you can see that if there's no keystrokes on no other packets classified as keystrokes within 7 packets on either side, we again flip that to not a keystroke. So that's the iterative mechanism here. As far as how do we actually do this? Well, number one, we have a typing speed threshold that we use in our basic exclusions at the beginning. And this, we've set it at negative 2.2, which corresponds to a typing rate of roughly 1,500 words per minute. And there's been a number of studies on the distribution of inner arrival times between keystrokes. And for instance, I know that Song and some others and their timing attacks on SSH found that rarely did you have inner arrival times that would correspond to anything exceeding more than a couple hundred words per minute. So that's been validated in other studies, and we'll see later on that is consistent with our work as well. Additionally, how much can this echo how far off can this echo be from so how far off can that yellow diamond be from the green diamond that we have in our plots? How different can they be in height? And so we take a look at that, and 0.1 seems to do all right there. And finally, we have to set the parameters for the classification tree. We did that using a test training paradigm. So that's how we go about looking at our tuning parameters here. This plot offers a little justification also for that choice of negative 2.2. What we have here is the empirical CDF for the inter-arrival timings of data packets. The top panel here corresponds to the inter-arrival timing corresponding to data packets from the client that were keystrokes, and these down here correspond to client data packets that were not keystrokes. So clearly you can see that when we look at this distribution here, this distribution is, these inter-arrival times tend to be much higher, and if we look at negative 2.2 here, which corresponds to about there, this is a basic exclusion we're using, so we're missing almost zero of the candidates. I mean, there's basically nothing that we're leaving out here. Whereas we are eliminating a lot of potential client data packets down here that don't fit the right timing profile. So we eliminate a whole lot, but we give up almost nothing with this exclusion rule. As far as the echo lag, this is a quick example from a number of our known connections here. And what you see here is that this was set at 0.1, and so 0.1 would correspond to, we want that inter-arrival timing to be between 0.1 and negative 0.1. So these vertical bars here are exactly what we want to see. We don't want to see points off to the side because that would mean that we're excluding things we should not be excluding. And when you look at these distributions, you do notice that there's a few points that lie out here, far to the outside, and these are keystroke times that are way off. And what this corresponds to are these are keystrokes that fall at the beginning of an epoch. So when you have an epoch begin, you might have had a whole lot of client data packets coming in this direction, and almost zero server data packets in the preceding epoch. And so you're going to have some, that first packet's timing characteristics may be slightly off. And that's what we see here. We see that those are the few places that we miss here, and those correspond to the beginning of our epochs. So again, this exclusion rule here seems to be all right. Finally, this is a little summary of performance looking across the trace 2 and trace 3 connections. When we look at it, we saw our effort here was to classify every client data packet as being either a keystroke or not a keystroke. And what this table corresponds to here is we've got the truth here. So not keystrokes, there were 1,988 not keystrokes, and there were 378 keystrokes across these connections. And when you look at it, out of the keystrokes we miss 9, and out of the not keystrokes we have 5 false positives. So 5 false positives, 9 misses. Our error rates seem to be fairly low here, and we did do a quick comparison with some kind of standard out-of-the-box algorithms as far as regression and classification trees and things like that. And our error rates seem to be about between 1/4 and 1/10 of their error rate. So compared to some just out-of-the-box type procedures performing the same classification task, we seem to do all right. One other point to note here that this is we've aggregated over both bulk transfers and interactive type connections, and there were 0 false positives as far as keystrokes go on the bulk transfers. So that was nice that we were missing where it was where it was important that it was nice that we were getting it right where we were supposed to get it right. We didn't want to be finding file transfers that had keystrokes. We've also gone and applied this algorithm to trace for that the data coming into the statistics department and leaving, going to the outside network. And when you first look at this is the what we have here. These labels are a little bit small, and But the first line here corresponds to SSH, the second is SMTP, and the third are unknown connections. And what you see here is almost 50% of the connections that we classify as having keystrokes are SSH, 35% or so are SMTP, and 15% are unknown. And so at first this is a little bit disturbing when we see, but again here we're just looking at connections that have any keystrokes. When we move one step further, we look at the performance as far as how many keystrokes are we finding in these connections. And this provides us a little bit better grasp on what's going on here. And when we look at this, we see that those connections that were SSH have far more keystrokes in them than those other protocols. So for instance, the SMTP connections that we found with keystrokes, these connections that were classified as keystrokes all of them had 2, with the exception of one which had 3 keystrokes in it. So there were very small numbers of keystrokes in these under the other protocols where we were missing. And actually, using the plotting tool, we were able to identify that there's a handshake that goes on at the end of the SMTP that produces a false positive as far as the keystroke goes. And we saw the same thing. There was one connection with IMAPs, and the unknowns again for the most part, the unknowns had a small number of keystrokes too. So that was a nice sign here that hopefully we're doing something that's all right. So we can make our connection level prediction a little bit better, and we do this by revising our prediction rule. We say maybe we shouldn't classify a keystroke connection as a connection that has just one keystroke doesn't make a keystroke connection. Maybe it needs to have some minimum number of keystrokes in there. And so, as an example of the direction to go here, we take a look at what if we made that 5? It seems like it's going to take 5 keystrokes to get something done anyway. And once you do something like that, you have about 90% of the connections. 90% of the connections with keystrokes become SSH, and a little less than 10% are those unknown. And we've gotten rid of the SMTP and the IMAPs, things like that. And so that's kind of nice. And it's somewhat promising as far as where to go from here. But again, this is a work in progress, so this is definitely not the final conclusion here. As far as our future work here, I think, as I just said, that we can review the classification rules for defining a keystroke connection. Additionally, we need to know what's going on with these unknown connections. What's actually going on with the unknown connections? Those unknown connections are protocols that we don't know, but there's got to be a way to investigate that. And so, hopefully, we will be able to work with the department and get a hold of sync this up with our anonymized data and bring these two things together and come up with a little more intuition for what we are seeing. And finally here, since this is a work in progress, I thought it would be, I wanted to open up to any suggestions or questions you might have as far as your thoughts on this or where to go from here. So I'd like to thank you very much for your time today, and yeah, that's the gist of it. Thank you.
Yeah, when you're actually logging this information where the packets are coming in and going out, where is that logger located? Is it on the server side? Is it on the client side? Is it at a router? Or
where's the network monitor located? Well, as far as I wish I could draw a picture here for you. As far as yeah, huh. Well, tell you what, I'll go through each one of the traces, and each one of the traces is slightly different situation. For instance, in the Leipzig situation, they had something between the department and the outside, and the instances of the connections that we manually created, that was we were running TCP dump on our machine, so the monitor would have been at one of the endpoints. And in the case of the department, the monitor was between I guess it was set up basically at the department, but just as you exit the department from the backbone of the department to the outside is where the network monitor is set there. Yes.
Did you look at all about any distinction in terms of distance or latency along that connection? So, for example, connection between here and overseas versus between two places on campus.
You're going to have your round trip times are going to be completely different, and so you're going to maybe see some that gets back into the keystroke sequence packet sequence form and what impact that has there. What we saw was that the inter-arrival times over those distances seem to have our green diamonds seem to overlap with our yellow diamonds. For instance, when we compared connections on campus with going across the country and coming back, our green diamonds and yellow diamonds lined up very nicely. Where the difficulty came up there is that we would see your keystroke packet sequence form as far as the data sizes, or as far as how they mingled. You might have a lot more variability in the packet sequence form. So, for instance, you'd have client data, server data, client data, server data, client data, server data, client ACK. Whereas if you've got the monitor right here on campus, every one of them is going to look like that standard textbook sequence that we are all used to. So that was where we saw the most pronounced impact, was the packet sequence form. But the diamonds seem to do fairly well over long distances. Any other questions?
One last question. There has been kind of work on covert channels and in security community and using timing channels for covert channels for communications. Have you looked at all at that area to see whether this would be useful as a way for identifying such covert channels?
Are you talking about some of the work like detecting stepping stones, things like that? I know there's a few papers along those lines, but I think I know what you're talking about. And we have done a little bit of reading in there, but we haven't really explored that direction so much.
Actually, one question I have, really for everybody is, so this all falls into the category of,
So this falls in the category of monitoring and forensics for network security to keep the bad guys from breaking in.
and so at this point in time, that whole area is in a state of tremendous flux, maybe is the nicest way to say it. Chaos might be a better word. So what is it that's happening? Well, the commercial area has developed a whole lot of tools for being able to go across your network and collect a lot of information from logs and bring that back to a security management station and then do things with the logs. So Purdue has actually had decided to buy a tool that will look at logins across the whole campus, and the tool then displays it. And system administrators can look at that to find patterns that they deem to be undesirable, whatever that might mean. So it's just a tool to look at them more effectively. Right now, like for example, in our department, the system administrator comes in the morning and looks at the log files. He can scan it pretty quickly, and then he'll see somebody, coming into a workstation that belongs to an individual who's logging into it from China. Now he sort of thinks about, of course he knows who the people are, so he's not somebody we are, but he knows who that individual is and says, well, yeah, I happen to know she went to China, so all is okay. So there's that kind of thing going on. The other kind of thing that's going on is this kind of monitoring that we see here, where you look at connections, and this is the direction that the Department of Homeland Security is taking. Their idea is, you stick a monitor on, and at the connection level, you look at what's going on, and then you can look over very large networks, like, when I say very large, I mean it's sort of an enterprise network that's, say, part of the Department of Defense or something. So the question is, there's our little group here. Who else, does anybody know anybody on the campus who's working in this area monitoring forensics? We have a lot of security work going on. But what about this particular area of monitoring and forensics? Do we have people doing this? Are there people who would like to do this?
The work, well, there's Mark Rogers, but his work is more kind of after-the-fact forensics rather than monitoring. It's like for law enforcement, you
Oh, yeah,
collect
yeah.
information and you want to figure out what that information means rather than
The
doing
white-collar crime person.
yeah,
Yeah,
rather than doing
Yeah, that's
the
different.
real-time monitoring.
yeah, that's a different area.
It's a very different world.
Right. So we're it? It's a daunting task, that's
Yeah.
why. I mean, we're looking for partners, let's put it that way. I mean, there's a lot of stuff to do here, and every time we collect, we get, you can very easily get a terabyte of data, in the blink of an eye, so it's a big job. Well, I'd like to thank Paul.
Forward to seeing you all next week. The sign-up sheet is